So today I'm going to talk about a new method that we have developed, which for the first time can characterize the mineralogy on a millimeter scale in situ and non-destructively over the anatomy of fossils. So we're all familiar with these beautiful Burgess Shale type fossils. I put a few up here with waxy morella. And Nick Butterfield in 1995 defined this type of preservation as the exceptional organic preservation of non-mineralizing organisms in fully marine siliciclastic sediments. So basically what you've got is organic matter is being preserved, compressed parallel to bedding in shales. And these fossils, as we all know, are of crucial biological importance. This is a sketch I really like, and this is the Cambrian seafloor in the vicinity of the Burgess Shale, and this is what it would look like if we hadn't have found the Burgess Shale. So what you've got is just the mineralizing organisms, trilobites, brachiopods, and it seems quite a poor diversity fauna. But if we put in all the organisms we find from the Burgess Shale, we get a much more complete picture of the ecosystem. We can see much more complex relationships. And in fact, ordinarily 86% of the fossils that we find in the Burgess Shale would not be preserved were it not for this exceptional preservation. The fossils are also of wide use if you're trying to reconstruct early relationships among animals, to understand how these groups first emerged. And recently we've seen just the exceptional nature of these fossils with visual systems and brains, these intricate details being preserved. So not surprisingly, these types of fossils have generated a large amount of research over the last few decades into how they are preserved. What are the processes that control their preservation? Because it's crucial to interpretations of their biology. So some studies have focused on sediment composition. Does sediment composition restrict decay? So other studies have looked at limited oxidant supply, low oxygen, low sulfate. And recently there's been a lot of work trying to characterize authigenic cements, carbonate cements, which sit in sedimentary laminae that sit right above fossiliferous horizons and may actually seal those beds to subsequent diffusion of other oxidants. But I want to return today to an hypothesis that was put out in the late 1990s, that some of these fossils were actually replicated in authigenic clay minerals. And this is a hypothesis that was put out in 1998 in Science by Paddy, Stuart, Kearns, and Briggs. And basically what they did was they looked at the elemental compositions using EDS on different Burgess Shale fossils. This is morella, for example. And they noticed that the elemental compositions varied across the anatomical features of the organism, such that it looked like the elements that were consistent with clay minerals were enriched on the organism itself, and in particular certain tissues, for example the stomach and the canals in the head shield, were enriched preferentially in elements like aluminium compared to the rest. So it looks like there was a tissue-specific variation in the clay minerals. And they used that to suggest that these minerals were precipitating early in diagenesis and forming some kind of protective impermeable layer that protected the fossil from subsequent decay. But this has one significant implication, which is if this really is true, then if we knew the mineralogy of these organisms, we knew how mineralogy of these that are now there, if we knew how that was formed, then it might give implications for the original tissue composition itself, particularly since these minerals seem to vary across tissues. However, there was a problem, and that problem was we didn't know the age of the minerals. So there are a number of authors that put out studies since then which have suggested the clays may not form early in diagenesis, but it may indeed be metamorphic. The Burgess Shale has undergone green-schist metamorphism, both in the Paleozoic and then later in the Mesozoic too. And so the authors found trilobite carapaces, for example, which were originally mineralized, calcitic, and they too now had clay minerals on them as well. So the clay minerals weren't just sitting on the organics, but actually sitting on mineralized structures as well. And this was compared to the coatings of other fossils throughout the geologic record, such as graptolites, which commonly have clay coatings. Those authors attributed the variation in mineralogy across the different anatomy to differential volatilization of those tissues at different points during the metamorphism. creating a physical space in which minerals could be precipitated, and because it was a different stage of metamorphism, they would have had a different evolving metamorphic fluid, which may have allowed different minerals to precipitate. But this hypothesis also has some problems, in that metamorphism happened tens to hundreds of million years after these fossils were deposited, and over that time, the composition of the tissues would probably have converged such that they may not have volatilized at different times. And really, nobody has critically evaluated the mineralogy on these clays, on these organisms. All we know is the elemental composition. If we knew the actual mineralogy, it might provide a prediction of how that mineral formed, and may allow us to, in fact, distinguish whether they are early or metamorphic, and actually may help us unravel some interesting insights into the original tissues. So we're using a new method, which is selected area X-ray diffraction. And we've done it on 2 specimens of morella from the Burgess Shale, from the Smithsonian. And this is an example of one of those specimens. And first off, we did exactly the same as what all Kearns and Briggs did, which was we mapped, using SEM, EDS, the elemental composition of the organisms. And we got the same kind of results, enriched in silica on the body, with aluminium again in the stomach, in the canals, in the head shield, and a little bit in the gut trace too. But what we've done is we've then done X-ray diffraction over select areas of the fossil. So we've narrowed the X-ray diffraction beam down to a 7 by 1 millimeter area, and that allows us to do in situ analysis on different areas of the fossil. Now, this is only possible because we're using a detector on an X-ray diffractometer, which collects at 250 times the rate of a regular detector. So for most of our analyses for one of these 7 by 1 millimeter areas, we would run our detector for about 6 hours. If you were to do that on a conventional diffractometer, it would take over 2 months of continuous collection time, which is impractical. So let's take a look at some of the results. First off, I'm going to show you that this method works. So we're going to compare an area of the matrix that we've done in situ using selected area diffraction to a powder diffraction pattern from a bit of ground up matrix to show that we actually get the same minerals coming out. And this is the powder diffraction pattern, and then this is the matrix. And you might say, oh, do those look different? Well, actually they don't. The peaks are in exactly the same places, and we have exactly the same minerals. The relative intensity of the peaks is different, and that's because when we're doing it in situ, we actually have orientation effects that preferentially suggest that some minerals are more abundant than others. This is not true on a randomized powder diffraction pattern. So we can't get quantitative data from this method, but we can know the minerals that are there. So let's look at some of the results. So first off, we're going to look at 2 areas. One is on the matrix, and the other is on the fossil. And the grey boxes actually show the actual areas that we've looked at. And what you'll see is the 2 diffraction patterns are exactly the same. If we look at what minerals are there, it's muscovite, quartz, and then minor amounts of chlorite and calcite and dolomite. These are the same minerals that have previously been described from sediments from the Burgess Shale. If we then go and look at this area of the head where we have the enriched aluminium, you might expect that might be different. And if you look at the trace, you're going to say, Ross, it's not different at all. It looks exactly the same. But let's just zoom in on one area of the spectrum. So we're going to zoom in on this area down here, and we're going to look at this 7 angstrom peak in particular. And what you'll notice is that there are actually 2 peaks there. So the peak is split. And that's because we've got kaolinite, an aluminium-rich clay mineral, enriched in the stomach and the canals in the head shield, which is not in the fossil and not in the matrix. So we've been able to identify what mineral is actually here in making this aluminium. So what does this mean? Well, kaolinite is an aluminium-rich clay mineral. It cannot be distinguished in XRD from its metamorphic product dicite, so we may have the metamorphic product dicite. It forms under relatively acidic conditions in early diagenesis, and unfortunately, it has a rather large it's stable under a large variety of metamorphic conditions. So it means that we actually can't distinguish, in this example, between it being metamorphic or it being early. We're still left with that problem. But let's assume, for the sake of argument, that it is early. And let's think about what this might mean. So aerobic decay decreases pH through production of CO2. Okay? And then the areas with the kaolinite must have had a lower pH because we know that forms under quite acidic conditions. Tissues that are less resistant to decay or have greater mass are likely to decay quicker or to a greater amount, reducing preferentially the pH in the local area of those tissues. If we look at what tissues, where the kaolinite is situated, it's in the stomach, it's in the canals, in the head shield, which connect to the stomach, and it's in the gut trace. Those are areas where you likely had more labile tissues compared to the chitinous exoskeleton, and they're areas where you likely had the most mass of the fossil. So it suggests that we might actually be able to, our analysis is actually working to find out something about the tissues of these organisms. So in conclusion, we've pioneered a new method of non-destructive in situ mineralogical analysis of fossils. I think this can be applied to a wide variety of fossils. We've been able to identify for the first time the mineralogical variation across the anatomy of Morella, not just the elemental differences. And this yields potentially the insights into the tissue composition. We're going to work we're working currently to try and further restrict the idea of whether this is metamorphic or early. And so we're hoping to apply this to other Burgess Shale type fossils that have a higher degree of metamorphism and to see if the mineral assemblages change in those situations. We're also using, now we have a good handle on what minerals are there, we're also using those and seeing what happens when we undergo maturation experiments with those minerals and see if we can gain any insights from that. I think it would be great to apply this to other Burgess Shale animals, particularly maybe others that have different minerals that might be more diagnostic of whether it's early or late. And finally, we've begun to use this, a similar method on Proterozoic fossils, this time not using X-ray diffraction, but using infrared spectrometry and using a synchrotron to actually measure clay minerals around Proterozoic fossils too. And so with that, I'll say thank you and invite any questions.